Yo, 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 think we're good. Happy day. Joe Zach here, doing another problem, except maybe I should say I'm going to attempt this problem because anagrams, so we can think of permutations, which is one of my kryptonites. Oh, maybe I should change my name to Kryptonite. Let's see if I can do that. Very important. Joe Kryptonite. There we go. Spelled incorrectly. I love it. All right. Okay, now I'm ready to start coding. I have enough procrastinating. All right, so this problem, we're going to find all the anagrams in a string. So we're given a string S and a non-empty string P. We need to find all the start indices of P's anagrams in S. Strings consist of lowercase English letters only, and the length of both strings S and P will not be greater than 20,000. Okay, so that's pretty big for both of those. The order of output does not matter. Okay. So in this example, we have S, which I guess is the sample. That's how I'll think of it. And P is the, I don't know. The P is the P. I'm not feeling very creative. The piece, it's the piece we're looking for in the sample. So we can see at index 0, we have the same letters that are in P. And the substring with start index 6 is also. Okay, so for a second there, just for half a second, I thought maybe I could just take the P and generate all the different permutations of it. And then as I go through S, I can just look up. But when they're talking about P being this big, we know the permutations are just out of control. So that's not going to work. So how do I know when I look at this string and this string if they have the same characters? One way is to sort both of them. So that doesn't really help me. I mean, I'm going to have to sort here once, so that's not a big deal. And log n, and we sort here, and then we do it starting from here, and starting from here, starting here. So we get n times n log n, which is even worse than n squared, n squared log n. So I seriously doubt this is gonna fly. So we got a problem. Whew. Well, let's see if this one reveals any clues about what we're doing. We got a small p here and slightly bigger s. So we can see that this is a permutation, also this, also this. So that's a good case to think about. Ooh, so let's take sorting out of the equation. You know, we talked about tries recently. Tries are a good way to look up if something exists. So what if, I mean, this is probably crazy talk. It's probably a terrible idea. But if we looped through this and generated a try ahead of time, so that would be using a tree data structure. So here we'd have like a, I don't know that I want to do on this. I think I want to do on this side. I'd have an A, B, and I'd have a BA. And over here, I'd say, hey, A, yep, that's okay. And then B, yep, that's okay. All right, now we start here. That's a B, yep, that's an A. So generating this for the try is going to be N. It's going to make our memory footprint also N. So, okay, that's doable. And now looking through here, we'd be looking up in the try which is the runtime is equal to the number of characters in P. So not the worst. And then we'd have to do it again and again. But the thing that really stinks is, like, if this was long, like if we come back up here and look at a longer one, we have to look at these 3 characters. And then we have to look at 2 of those 3 again. Like, how can we take advantage of the fact that we've already done some work on some of these? Oh, that makes me think that this is a dynamic type problem. Or that, rather, I guess I should say that this has a dynamic solution. Oh boy. It's gonna be a long night. Say, give it 30 minutes from now, so 10:03 my time. I'm gonna give up and look at the discussion. Until then, I'm gonna give it a good go. We're gonna do it. So, if I were trying to devise a dynamic solution for this, I would probably keep some sort of table or memory structure. And what would I do? Would I keep like a data structure for all of this with either a 1 or a 0? Oh, okay, that's interesting. So what if I kept it 1 or a 0? And as I loop through this, I just look up whether or not this letter is contained in here. So I would say yes, yes, yes. And if I get to 3 yeses, which is the length of this, I could check to see if all 3 exist. Okay. Okay, that's interesting. So I'd say 1, 1, 1, 0. So as soon as I see a 0, I know I could kind of forward this whole thing I'm doing. And again, say 1, 1, 1. Now here, I would check and I would see, no, I got too many B's, not enough C's. Let's go ahead 1. Same thing, too many A's. 1, 1, 1. We will go check. Yes. So, what do I think about that algorithm? So first I'd have to go through and split this up into a lookup structure that allows for fast lookups, like a hash table. Hash set would be not a hash set, actually. I would want to do a hash table with a count, because presumably you could have duplicates. And then over here, how many times do we look at the same letter? In this case, we're going to look at this same letter P times, which means our algorithm is going to be S times P. The length of S times the length of P in the worst case scenario. So that's, you know, there's 2 different variables in there, but if you imagine they're both the same size, then basically we're talking about an n squared algorithm, which is not fast enough. So, I don't know, I'm going to play with this a little bit more. Let's take this to the example area and kind of think a little bit here. Let me check the chat. All right, chat is not working. There it goes. Cool. I tried fixing that today. Yay. Okay. So if we went through here and kept a running sum, because that seems to come up so often, we go 1, 2, 3. Boom, boom, boom. We could do our more expensive check here and to see if we have all of them. Okay. Then what? We go to the next one. We can see that this is not a member. And so we reset our count back to 0. And over here, what? Start a count again. 1, 2. I'm still struggling with how to deal with this. I don't want to keep changing the values in here to keep track of how many letters I've seen in the cases that we have duplicates. So, I don't know, let's say somehow I managed to get around that problem, say 1, 2, 0. Then I know, I can't say 1, 2, 0. Yeah, that's pretty yucky. Pretty yucky. So here, I should see that I have 3, but because it's missing a letter, I have to go on to the next one. Which is strange, because in this case, it means I need to keep this number. But I don't really know how to tell that. That's weird. So the only way I can figure out this number is by backtracking to see which number is erroneously duplicated. So that's making me not love this running sum idea. That feels wrong. What if... I mean, I'm really trying to figure out how I can run through these numbers just once. So I could say yes, 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 no, yes, 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 no. Then what? What can I do with that information? What does this tell me? Okay, what if instead of 1 or 0 for yes or no, I kept the index? Does that help me? So here I would say 3, 2, 1. Okay. Interesting. So it's pretty easy to know if these 3 numbers represent the right values because I can add this up. So when I'm done, I can add my indices. So I could see that I've got 6 here and 3 letters. And between those 2 pieces of information, you have 3 letters and they add up to 6. Then I know there's no other way to... That's not true. 2, 2, 2 also adds up to 6. Dang it, this is going to be a problem. So far, telling if it's been an anagram hasn't really been the hard part. It's been trying to figure out how to look through this the least amount of times. Okay, let's think about data structures. We've got an array. I don't think that really helps us. Linked list. If I had a stack, would that help me at all? If I said C, B, A, I could see that the length of my stack equals 3. And I could look to see if all these items are represented in the results. Yes, so we record that index of this one, and then clean this stack, wipe the stack. You see E. We shouldn't even push E on the stack. I see E, and I should move on. So what if for our stack, we recorded the indices. We said 0, 1, 2, and we can look that up and see that it matches. So our result equals 0. And then we clear the stack, and we set our, start equal 1. Okay, so then our stack goes B, A, or I should say 1, 2. Let's try it like this. I like that better. And then when we get to E, we know we can clear the stack. And now set the start to the index of E plus 1. So from here, now we go B, A, B, not a match. So maybe linked list isn't so far off, because then we could just pop the front off cheaply. But how do I know it's the first one that I can get rid of? What if the ones I pushed on were A, B, B? If it was A, B, B, then I would know I'd have to remove this one and remove this one. So that's interesting. So I like that the linked list makes it cheap for me to remove items from either end. However, I still have the problem where I'm looking at every number in S potentially P times. So if you imagine, it's easy to see the problem when you think of it something like, I have this as my S, and I don't know, this is my P. Or no, let's make it even worse. There we go. Let's see. Right there. How many times is this string in this one? Well, it's there, and there, and there, and there, and there. So I don't know. That linked list, it's starting to seem more appealing. Let's try a smaller example of our worst case scenario. Our start is 0. Our queue is empty. Our results are empty. So step 1, convert P to a hash map with counts. So basically in this case it'd be A1, B1. All right, we're starting at 0, so our queue goes B, A. At this point, we can look up both items and know that our hash map has been totally fulfilled, so we record a 0. We increment our start up to 1 and clear our queue. So now we're looking at these two. So we push an A and a B, record a 1, because they both match, clear our queue, start at 2, add a 2, start at 3, Add a 3. Clearing the queue is not right. I shouldn't clear the queue. Let's take another look at it. This time without clearing the queue, only removing part of it. Does that help us? So here we start with the B. We see that it's in there. We add the A. We see that it's in there. We see that our hash map is fulfilled. So we record a 0. Now, let's not change our start just yet. Is that right? No, we have to change the start. So we start, change the start, and then we have to remove the first item. But we could keep this one, which means we could start, we could change this. No, it still has to be started there. The thing is, we skipped a right here. It's not a big savings. We add the B, we see that it goes on, goes here, remove the first item from the queue, and then A, and so on. Remove the first item from the queue. What does that do for us? Our queue length will never be bigger than our P length. I like that. But no matter what, I'm still looking at this, each individual letter, this many times. Is that right if I keep it in the queue? So after I saw this, I discarded this. I kept the A, so went on to the B. It's kind of too hard to see. What if we did this? Start at 0. So here our queue would go CAB. We record the result. We remove the first item, increment the start. But the item that we're looking at is actually, it's always like start plus the length of queue. Or maybe I should say current index is equal to the start plus queue dot length. So I'm always looking at start index, but start is what gets recorded for the result. Okay, so here we remove the C. We've got this in our queue, and I don't need to look at these again. Now I can look at this, and assuming I've got a decent enough way to kind of look up in my hash set to see if it's been accounted for or not, and our queue gets set to this, we record the result, we increment our start, we cut the first, we take the first one off of the queue. Oh, here again. We add the A in. I think this is pretty good, actually. This might be a good solution. It means I don't have to keep looking up these things over and over again. Basically, I can kind of keep a temporary P around, which knows which items I've seen and not seen. So this approach does hinge on that. So I need to make sure that I can account for that. So let's try this again. This time let's throw a couple bad ones in there. Sure. So I'm looking for ABC in this string. How many times? We start at 0. We got nothing in our queue. We have nothing in our result. First off, we convert to a hash map with the counts. And this time we'll consider the hash map as we go along. All right. So we come in here. So maybe I'm gonna put the hash here. It's A1, B1, C1. So we add the C to our queue. So our hash temporarily sets its C to 0. So somehow I'll have to be able to reset this, I think. So maybe each node kind of keeps its like initial value as well as the value it's currently at. It's not too bad. I think that'll work. Okay, so I like this. So this is what we've got in our hash. We go to the next item. So we add the B, so we reduce it from here. That's fast. Order 1 operation. Okay. We add the next one. So it was actually supposed to be an A, whatever, doesn't matter. Now at this point, the hash has been completed, but how do I know the hash has been completed? I could loop through the hash, but I'd really rather not do that because it could be large. Is it large though? Does it say we're only dealing with lowercase? Yeah, only lowercase, so 26. 26 letters, so we'd have to loop through potentially 26 letters to say 0, 0, 0. Maybe we could speed that up. That's constant. So technically, we don't have to worry about it. It doesn't grow with our integer. But potentially 26 checks to see if it's empty. Maybe we can figure out an optimization there. But at this point, we can see that our hash has been fulfilled. That's fine, that's fine. Our result, now we record the start index here. So this becomes 0, this becomes 1, this is our next contender, and we remove the first one off of our queue. And when we remove this from the queue, we go up here and increment it. So say we're looking for a C. Okay. So we come in here, and now on our queue, we add a capital Z, which is invalid given the input, but it helps us kind of distinguish. You can imagine that's lowercase. So here we have a different case where we know that these two are dead forever. If we see an item not in the hash at all, we can fast forward to its index +1. So here we know that index 1 is invalid, index 2 is invalid, index 3 is invalid, so now we're looking at index 4. So I liked how that felt, but we do have to reset the hash, which loop through 26 times and replace these values. That's pretty grody, but not the end of the world. We also clear the queue. Okay, and that's good. Now we have a B. That's fine. Redecrement our hash. We have our A. Okay. So we decrement our A. Now we get an F. So same thing here. As soon as we see the F, we can fast forward to our index. I guess I could just say Q to add Q length plus 2. Hey, what's up, Sorov? Another counter? Yeah, I'm thinking about using a linked list. I don't know if you've seen this problem yet. I'm trying to approach it like a counting problem. I don't know if that'll actually work. So we just set the starting index to 8. Counter equals the length of the hash map. Decrement. Oh, the length of the hash map. The hash map has quantities in it because this P could have, I don't know, say 2 C's. So let's look at this example. So the initial values. But I don't know, that's interesting. Maybe maybe I could think of like a hash set that allows for duplicate values. A, B, C, C. And maybe only decrement if the C becomes 0. One thing I have to be careful of when keeping the counter is right now when I see something that's totally not in my my hash at all, I can fast forward a couple steps. I wonder if there is a data structure that allows for a hash set with duplicate values. Change the value if the hash map at the character equals 0. Oh, that's good. Yeah, good call. Okay, yeah. Yeah, totally. So that would be a better way of checking to see if every item in... So I don't have to loop through this. Yeah, good call. So keep counter of items left in the hash map. If empty, score. So algorithmic complexity. So for this solution, let's see if it's viable. There's a couple different steps. There's constructing the hash. Doing the hash of P. And then, so that's going to be an order n operation. We could end up with a pretty big hash table, but worse things have happened. Space complexity, we're looking at an order n in order to keep track of all the items in P. And I'm basically reducing, you know, it's really order P, but I kind of figure since P and S can be the same size, you might as well just call them n. Just kind of simplifies things. So it scales with the input size. Worst case scenario, it's O of n. Now we do loop through all of S. And we do hash table updates, which are order 1. We do lookups and updates. And we also, so hash table lookups, updates. We also maintain our queue. Queue insertions, shifts, or what do they call them? Removals, whatever. Remove first. That's also if assuming I keep track of. No, I mean that's just fine. I can just use the built-in queue, built-in linked list. Remove first. So that's order 1. So O1 here, O1 there. This is O of n. So what? We also have our result, which is also order n, hash tables n, but ultimately it's space complexity of order of n, and this just boils down to order n. So I think that this is a good algorithm. So the complexity, algorithmically speaking, is scales linearly with the input size, and so does the space. So there's a couple constant multipliers in there that I'm glossing over because I can. So I think this is going to work. Always good to figure that out before you start. This is definitely one I'm going to be doing in IntelliJ. I don't think there's going to be a lot of code. I would say this is a pretty complicated problem, though. It feels like I'm missing something. Like whenever I have a lot of different moving parts, first of all, the debugging time tends to be high. Well, I don't want to create a new project. So I'll have to be really careful with my tests. But I also feel like I'm probably missing something. So it's kind of uncommon to have multiple data structures in this kind of problem. That's not unheard of. What's going on here? Oh, IntelliJ. Usually does better the second time around. I am several versions behind though, I realized recently. Come on, you could do it. Alright, cool. Should be up now. We'll call this one. Oops. What? Anagrams. All right. Here are my notes. So let's do this. All right, so step 1, we're going to convert P to a hash map with counts. So P dot map. Can I do that? What about a flat map? Oh, didn't we say there's grouping by? Yes. Group by the character of each string and then count each count. So there we go. We'll call this pmap. I believe that's correct. Okay. Now pmap. It's not enough. It's not enough to just know the count. So on here we'll also map to a data class called I don't know. Letter let's see. Geez, I don't know, frequency. and I'll have a val called initial, and it's a value, it's a val, it's a not changeable, immutable. We have a var current, which is also an integer that represents the current count of it. So here we'll basically just do our map, and we'll return a frequency object that has our current value, and then current, we'll call this current needed. Needed? Is that better? Okay. Oh, and we need it dot key to frequency. This will be dot value dot value, or another way we could have done this is we could have said map values. So we can leave the key the same, and then we can just say this. Okay, that looks pretty good. And then I don't need that, do I? I do. Okay. Fine. Okay. I think that feels pretty good. So now PMAP has characters to frequency. So maybe I should call it like character frequency. Anagram frequency. Okay. I'm kind of tempted to make this a whole object that keeps track of its own state. Let's do that. So we'll have a class called anagram frequency, because I think we're going to end up with several moving parts here. So let's have its frequency class be private. No one needs to tell us about that. And if you give us a string, then we will do the rest. We will keep track of our anagram frequency. What can you do with this class? I don't know yet. Val frequency equals an anagram frequency, and we'll give it a P. Okay. We need a var for our start index. We can start it at 0. Our current index, also 0 to start. We need a queue, which is going to be a linked list of with characters, I guess. Chars. Okay. And then we have our result indices, which is going to be a list of integers. Okay, and this will line up with what we're returning from the function. So down here at the bottom, we can return our result indices. So there we go. That all looks pretty good. I don't like having my vars mixed in here with things that don't change, so we'll separate those. Oh yeah, we need a counter for items left in the anagram frequency, but we're going to have the anagram frequency own that. Private value, private var, which is initially equal to p.length see items left, and we'll start with p.length, and we need to be able to reset this as well. You know, I kind of just want to just rerun this whenever I need to reset. Not the fastest thing in the world. Yeah, it's not. It's not. Let's just do it this way. It's fine. We also need the length, so we'll do it like this. The val of I don't know, p length. We'll do it like this. So this varies. Let's get these guys up top. So that we need a method for resetting. Reset. And when we reset, we will go through anagram frequency, and we will set it.value.current needed equals it.value.initial. Also, we will set items left equal to p length. Okay. Then we can have a function named satisfied. Which just returns items left equals 0. Okay. Now we're not ever decrementing items left, so we have to do that. So maybe we have a method named something like use, where you give me a car, telling me you're trying to use that, and I either say okay or no. So if anagram frequency dot contains value, if you have that value, should be mentioned input type, blah blah. Okay, we'll fix that in a minute. Maybe a boolean. I don't know what the return type is going to be yet. So if it contains the value, then this at the value dot current needed minus minus. What if it's less than 0? There's 3 states. We either don't have the item at all, the character at all. We don't have enough of the character, or are we good? Maybe we'll do an enum or something. This is getting pretty lengthy. I don't know what enums look like. Not enough. Or, okay. I'm gonna call this use state. I don't know. It needs to be public though, or package, whatever. Okay. So, if it contains value, then if it has enough is greater than 1, then what are you complaining about? Oh, I can't if that way. Fine. If it's greater than 1, then we're going to return OK. Alright, and we are also going to decrement items left. And also, we are going to what? Anagram frequency at C dot what did I call it? Items left. Current needed. Initial or current needed equals itself minus 1. And then we're good. Else return use state dot not at all. And here return use state dot not enough. Okay, so everything returns value. This can be more Kotlin, so let's lift that return. So I do modify items left here if you take it. What do you tell me? No. Just do it. It's gonna work. Fine. Can I do minus minus here? Minus 1. Why are you squiggling at me? Non-null assertion. It's fine, trust me. We just checked it. Type inference failed. If this at C is not equal to null. Okay. And fine. Map.get with non-null assertion. What? Whatever, I'm ignoring this. I don't know what the deal is. I don't know what's squawking at me. Alright. Satisfied is never used. Call it is satisfied. So I don't love that my use method changes items left. But I can get over it. Alright, we got some private stuff, we got some public stuff. So, I'll test that in a minute. But we no longer have to do this. Okay, so now this algorithm becomes for var I equals 0. I'm just going to do things old school and then we'll adapt it. I less than... Ugh, fine. Do while current index is less than s.length. What we'll do is we'll tell our frequency, and we'll try to use it. I don't know. I don't know what to call this. So we need a better name than frequency. It'd be like P tracker. I don't know. I'm gonna change that again. I can tell. We'll try to say letter equals s at current index. And we have to remember to increment current index. So here we're gonna use letter. We'll get the result. Or maybe status. And then based on the result, if status dot okay. Okay. I'll put this on the left so it'll read a little nicer. I think it reads a little nicer anyway. So if it's okay, then check if we completed the frequency. We'll come back to that. Else, if anagram frequency dot use state, we're going to be able to use a with statement here. It's kind of cool in Kotlin. Hopefully IntelliJ will tell me what to do. If it's not at all, then we have this use case we talked about up here. Where if we see an item not in the hash, I'll fast forward to index 2. Start index plus q dot length dot size plus 2. I mean, we could also just say like current, rather this isn't, fast forward means start index equals current index plus 1. And then also the current index stays the same. So it'll get incremented here. So we don't have to worry about that. Okay, equals status. Else, there's only one other state left, which is state where we don't have enough. And if we don't have enough, then we need to remove the first item off, first item from the queue. Remove first. And when we do that, we need to tell our p tracker dot add back, I guess. Add back whatever value we get from here. Does this actually return a value? Yep. So we'll remove the item and we'll add it back, which means we need a method here called add back, which is the opposite of use. Fun add back takes in a character, and what it will do, add back, is we will take our frequency at this character. We know that it exists. Current needed equals current needed plus 1. And also our items left needs to go up 1. Okay. So we remove our item back. Okay. Now, one other thing missed here is clearing the queue. Queue dot clear. Does that do what I think it does? Yep. So it wipes our queue. From the queue, yep. We add it back. I kind of want to frequency dot use state dot not enough. Kind of want to promote that one. And then here, this one can be the else. I think that reads a little nicer. And then we remove. So now the only thing we have left to do is what happens if we have successfully completed. So if we, in here, we can say if anagram, whatever this thing was called, p tracker, is satisfied, then what? Result indices dot add push. How do I add to my, should have been a mutable list of int dot add. We can add our item, which is going to be the start index. So the only time we ever increment our start index is when we get a successful result, in which case we increase it by 1, or we fast forward in case we've seen something bad. So check if we completed. Okay, and when we do this, what needs to happen? We add our item. And then what? We need to remove the first item off the queue and add it back to our frequency tracker. So it's aware that that item is now required again. I'll increment our number, update our hash map. Okay. If the status is not enough for the number, what needs to happen here? Well, the start index needs to increase by 1. And then we need to add back the first item that was in the queue. Okay, that's good. In here, so start index goes up, start index goes up. Start index goes up if it's satisfied. I think it needs to happen no matter what. No, that's not true. The only case where the start index doesn't increase is if we see something we like, but it's not enough to satisfy it yet. Which also means we shouldn't add the item back unless we are incrementing. Is that right? I think so. Okay, I think this is it. Done. This is a long one. Nobody's calling reset? That's not right. Somebody should be calling reset. Reset happens when we see ptracker.reset. When we see a totally bad letter, we fast forward. We should just reset the whole tracker. Okay. Now everything should be called except for this method, find anagrams. Okay. I'm gonna go ahead and bump this helper class down. And then we'll write a couple tests. Probably a lot of tests. Oh, fun. What am I gonna test here? I don't know what I'm testing yet. Geez, I don't know. Okay, so there is our sample. P tracker. What do I want to do here? P tracker dot is satisfied, should be false. So maybe we'll call this one like check initialization, and we'll be lazy and just have a couple basic tests. Assert false. Sure. You should not be satisfied. All right, let's see if that just works. Taking a while. There we go. All right, yeah, that worked. Good. I had some private variables. I'm going to make those non-private because it's going to make my testing easier. This is not something you should do in production code. This is not production code. Let's see, assert equals 3 for P tracker dot items left, and also P length. Okay. Let's try one with duplicate letters just to make sure. Okay. What else can we check? Dot frequency at A should equal 1 and B should equal 2. And if that's good, oh, come on. The value of the type parameter K should be mentioned in input types. That is because A is not a character. A is a string. All right. It's not null. You're not null. Trust me. Let's see what the error message says. Cannot infer type T in function. Blah blah. And int string. It's not a string. I told you it's not going to be a string. Fine. How about that? Grouping map. Oh, it's because it's a complex object. That's okay. Fine. It wasn't the compiler this time. Dot initial value should equal 1. Also, its current needed should also equal 1. And down here, your initial should equal 2, as well as your current needed. All right, good. Initialization is good. All right, so what else can we track here? So now, let's try using up the A. Result equals. We'll call this function check use. Sure, we'll try to use the letter A. So call this a successful use. Single use. Assert equals. Anagram frequency dot use state dot okay. What else? Our result dot not result. Our P tracker at frequency for the letter A its initial value should not change. However, its current needed should change to 0. Its satisfied should still be false. And I'm just going to go nuts on testing this stuff because this is going to be the tricky stuff that I really don't want to waste time debugging later. So I'd rather just do it up front and make sure, totally sure that it's all good. Assert. The items left should say 2. Alright, this is going to work. No! So here I got a not enough. Alright, so let's go look at our function. I should have hit Control B. So it's not equal to null. And I said your current needed should be greater than or equal to 1. Good catch. Good catch. I'd much rather catch that now. Okay, good. Awesome. So now let's try and use a multi-letter. Multi-use. And we'll try using a B. Now our initial value at A should not change, so let's leave it. Let's leave that test in there. Now our B should go down to 1 for its current needed, even though its initial was 2. So A is unchanged, B started at 2, is now equal to 1, still not satisfied. Items left should still be 2. Okay. Awesome. Now let's try using all the letters. See how that goes. Get ABB. Wait, before we do that, let's try asking for something we can't. So if we do that, the result should be not at all. And hopefully items left is unchanged and satisfied. I'm not gonna bother. Okay, fine. I will bother. ptracker dot satisfied. This is the definition of how not to write unit tests, by the way. These are all like having multi. I think I'm fine with that. However, these tests are so brittle because I'm running multi, so I don't like that. What does he call this? Check a failure. We're going to look for a letter that we don't have. Do lowercase. We should get not as all. We should still be satisfied. Everything should still exist. Okay, cool. So then the last thing is to, well, no, two more tests. Check not enough case. So let's use a B, and let's use another B, and let's use a third B. And I don't care about those uses. Okay, this third one should be not enough. We are still not satisfied. Our items left should be 1 though. Okay, awesome. Alright, so one last. Let's try the happy state. Let's see. Check everything. Wait, check success, we'll call it. So if I have ABB, then I should be able to use A, B, B, and my result should be okay. My satisfied should be true. And my items left should be 0. Awesome. Okay. So what else is there? There's reset. Collapse this for a second. So this is really the bulk of our work here. I need to check add back and reset. Those are pretty minor though. All right. Let's call this one add back. ABB, sure. So if I create my item and then I use an A and then I add an A back, I'm not worried about trying to error check here, so I'm going to rely on that other method to be correct. There's no return from add back, is there? Nope. Okay. So our p tracker frequency at the letter A, it's not null. Its current needed should equal its initial. So true. Oh, it's only one. Whatever. Okay, yeah, so just say that the current needed should equal initial. Okay. Okay, and let's do one more test before we add it back, just to make sure that it's, here should be 0, and here, I'll just do this, should be 1. This should be current needed. Alright, cool. I should also make sure that the value for our items left should equal 3, and here it should equal 2. Okay, pretty sure that's working, but I don't want to do this again. Alright, cool. Reset is the last one. So here, if we use the A and then reset, I'll go ahead and be extra careful. So after we use the A, we can see that, you know, I'll just use all of them. Use A, B, B. We should see that we're satisfied. True, whatever. And then when we reset, we should see false. We should see 3 for the amount needed. Left, items left. What else? Let's make sure that our that your frequency at each letter has been reset to its initial value, which is just that. Current needed. Current needed. Alright, no nulls here. This is called test reset. So we did find one bug. Assuming this works. Alright, cool. So let's run all these babies. Alright, look at all those beautiful checks. So I feel really good about our class here. We tested every method. Use, yep. Reset, yep. Okay, we thought about it several times. I think we're just plain old good there. Now for find anagrams. I kind of think we should just try a couple. Maybe I'll put the test up here. I'll put it up top for now, sure. Find anagrams. Solution, sure. Ooh. Let's have it outside the class. Solution dot find anagrams. You know, all these tests should have been whatever. I'll fix it in a minute. I'll put them in at the wrong level. Okay, so find anagrams takes 2 strings. Let's go ahead and grab the examples over here. So this is our S. Whoa. Oof. And ABC is what we're looking for. And I should get a result. Call this actual. And we should get a 0 and a 6. So actual dot contains an element of 0 and a 6. True. Okay. I should make sure I don't have anything else in there. Dot length size. Okay. So the chances of this working the first time are very slim. Okay. No such element exception. All right, let's debug this thing. So we hop in here, we create our P tracker, feel good about that. Create a new queue, create our result indices. We have start and current. Okay, our first letter should be the letter C. Okay, first letter an S. We're gonna try to use it. It should be successfully used. Oops, I stepped into. Okay. So we're gonna hop into here, but we're not gonna be satisfied. So we should just continue. Yep, and we increment our current status. Good. Okay. Same thing should happen here. So we should go down 1 line. Now we should skip to the end. Yep. All right, cool. Same thing should happen here, except now we are satisfied. Good. So we add the start index of 0. Okay, awesome. And then we are going to add our first item back from the queue. When do I add to the queue? Right now I'm never adding to the queue. That's incorrect. So in here, regardless of whether I'm satisfied or not, I should always add to the queue. All right, let's try that test again. Expected value to be true. All right. We'll go ahead and set a breakpoint here, and we should whip around to here. Whip around to here again. Now, if we go through this time, yes, you should also be satisfied. Okay. So we add back the first item in the queue. What does our queue have in it? It's got a C and a B, so we should add a C back. Okay. So when we go to add our third letter, which is the A, we should see only the letter B in there. So that's perfect. Okay. So what went wrong? We have the number 0 in here. Okay, so we never add the 6. So I'm thinking the problem is probably off by 1 error, I hope. So now the letter we're looking at is E. E is not in P. So we should jump down to here. So our start index should become 4. Is that correct? 1, 2, 0, 1, 2, 3, 4. Yeah, that's right. So that's where I was kind of hoping the error would be. Start is 4. We reset our queue so its size is 0, and we reset our P tracker, which we tested thoroughly. Current index. Oh my gosh, this song. I think I hated on this song last time. Whew. Okay, sorry. Jeez. All right. Now we're looking at a B. What's in our queue? Q is empty. Okay, and B is good. What is? I forgot what our input looks like. So B is good. So B should get added to our queue. Okay. Come back around. Now we've got an A. That's also good. So you're also added to our queue. Awesome. Now we've got a not enough problem. So here we should hop to this condition. Does that happen? Yes, it does. And so we tell this thing, hey, go ahead and remove first, add your B back as available. Oh. But I'm not adding this item to the queue. Ooh. Okay, I can deal with this. So in this case, I'm saying we don't have enough to satisfy. So what should happen here is this item. Well, dang. This is a little bit more complicated. If the first item in our queue that we're about to remove here is equal to our letter, then we should still add our letter. So let's write this down. Removed letter. So let's go ahead and get this out of the queue. Now, if removed letter is equal to letter that we're looking at, and we've got a special case here where we can swap these. So we shouldn't add back. We should leave it off. So let's try this again. So if the remove letter is different from, I should say, first in queue. First in queue. If the first in queue item is not equal to the letter that we're currently working on, then we should add this item back, and then we should increment our start index. However, there's a special case here where if our item, the first item in the queue is our letter, then we should go ahead and leave it off. But what we'll do is we'll still remove this from the queue, but we're not going to adjust our numbers because the numbers are the same. So we're basically swapping the first one for the last one. And now we're going to get the right answer here. No! Let's see what answer we actually get here. Alright, fine. We'll go through this. So our current index is 6 here. but our start index is 4. What does that mean? 0, 1, 2, 3, 4. So we're looking at a BAB situation. So this is our case of interest where our start index equals 4 and our current index equals 6. I should have still changed the start index. I messed up something else here. Else start index should increment by 1 either way, basically. All right, let's try that again. Not wholly confident in that just yet. Okay. Let's fast forward to index 4 because everything's good until there. 3 and 4. And here our current index is 4. Okay. Our start index is also 4. So this is the first time we're at 4. So what happens here? We go 4 and 5, and then next we should go 4 and 6, and at this point the next iteration should leave us at 5 and 6. 5 and 7 rather. So if we loop through this, oops, went too deep. Okay, so now it should hit this first condition, or rather it should. Yeah, it shouldn't do that, so that's what I wanted to happen. So now our start index goes to 5, and our current index will also get incremented to 7, which is what I wanted to see happen. So 5 and 7. So what I want to see happen here, let's see what the letter is. It's the letter A. So we got BA. A should erase that number, which should increase the start index to 6 and the current index to 8. Does that happen? Okay, this should get skipped. Right, yep. What's the state of our P tracker here? I'm a little bit worried about this not adding things back. Or I guess we should look at our queue. So our queue has nothing in it right now. And I think that's out of sync with our progress tracker, P tracker. Yeah, the P tracker thinks there's only one item left, but somehow our queue has nothing in it. And that's because I only add to the queue here, which is not correct. Because in this case, the else case, the one where I'm just simply using the value from the beginning, I need to enqueue my letter again. So now let's run this test. It's going to work. Excelsior. Excelsior. Let's try this one. Oops, too far. I forgot my test was up here. Alright, so in this case, there's our whatever. There's our whatever. We should get, let's get the right values. A, B, 0, 1, and 2. Alright. Go ahead and name this like this. And I think we're good. I think it's going to work. Oh, it doesn't like the colon. Fine. Okay, good. I think we got a winner. Alright, let's do a little bit of cleanup, and then we'll try this thing. Tests at the bottom. I do have some tests that were in here that shouldn't have been. Okay. All right. So we got our class solution, and it has one function and one internal class. Okay. So let's try this. Fingers crossed. We run the code. Okay, we got the right answer. And let's try submitting. I don't think we have to worry about anything where like P is bigger than S or anything like that. Like we could run time error. Maybe we do have to worry about that. Yes. So in this case, string index out of range. They gave us a blank and an A. I was thinking they wouldn't do anything dirty like that. I was wrong. Okay. So they did something like this. And I should say the actual size is 0. Instead, we get an error. Index out of bounds. So what happened here? Oh, I gotta do while. I just changed this to a while loop. So while current index is less than, so that'll be 0 is less than s dot length. I think I'm just gonna leave that, and then up here, that seems kind of silly. Why am I doing that? Shouldn't it be less than or equal to? No, it should always be. Okay, so if I move this up, yeah, then it's fine. While 0 is less than 0. Alright, everything should work. Yep. Okay, dirty trick there. Dirty trick. Thanks for keeping me humble, LeetCode. Wrong answer. I said 2, 3, 5, and they expected 3, 4, 6. How did we get that far off? This looks pretty standard. Oh boy, these are the ones that really scare me. Hopefully it's just off by 1. ABC. And you tell me you need a 3, 4, 6. True. 3 actual dot contains. Sure. I'm sure there's a slicker way to do that. Well, what happens? Nope, jumped too far. So what do I really want to see here? So my start index is 0. Alright. So I don't really care till index 3. No, I want to see index 2 actually. That's the one where things first go wrong. Because I somehow say 2. Did I read that right? I say 2 and they expected 3 to be the first match. And if we look at the input, why would I say 2? AAC? Okay. I think I have an idea. This might be okay. So we come in here, we get our letter. That's fine. Oh, let's walk through every one of these. So I say A is good. So this one is rather boring. We just add the last item to our queue, and we tracked it when we used the function use. Come back again. Now we've got the letter A again. A is only in our output. No, it's the letter B. Okay, I'm sorry. So this one should also be fine. This one should be boring. We'll just skip until we get to current index of 2. Now here is where we see an A. And our troubles begin. So I come in here and I say use. Oh, look at that. Even though items left is... Ooh. This function is not good. I see, I see. So here, at index A, we have a value of what? Current needed of 0. So it's going to come down here and say not enough. Is that correct? Yep, items left should not change. We still need 1 left. The frequency should also not change. So yeah, we should just return not enough. That's good. Okay. Okay. So status is not enough. Good. So we come here to not enough. We say, okay, hey, queue, get rid of the first item in your queue, which is an A. Okay, is A equal to A? It better be. A97, A97. And then we say, hey, P tracker. Why am I not adding this? This is wrong. This is wrong. If the item is not equal to, that's a not. They are equal. So because they are equal, I leave P tracker alone. And I add this item to our queue, which should only have the B in it now. B. That's good. Now I do increment the start index, which is good. I say the first winning item can be 0. Or 1 rather. Okay. Fine. So now we're coming back in here. Our start index is 1. Our current index is 3. So we're looking at 0, 1, 2. We're looking really far out. How did that happen? Oh, because we're looking at start index 1, 2, 3. Okay, so that's fine. So that's another A. So what's going to happen is we're going to hop down. We've got another not enough. So we remove the first item in our queue. So we're going to remove the B. And the B is not equal to the A. So I'm going to say, hey. This item is now required again. We're going to add this item back. And we come in here. We'll say the current needed for B is going to increase again. And then items left will increase. So let's see what that looks like. So now the frequency chart for item B, its initial and current needed should now match. Okay, that's good. And items left goes back up to 2. Also good. Okay, I'm happy about that. Let's say your first available start index is going to equal 2. So now we're looking at letters 0, 1, 2. So we're looking at letters AAC. All right. Let's come in here. Our letter is equal to C that we're looking at. We are able to use that one. Let's see, what does our P tracker have anyway? Items left is only equal to 1. What item do you need? I believe you have an A, yep. And we know you have a C because we just checked. So all you need left is a B. And so if I look at the queue, I should see an A on here. Where's my queue? And I'm about to add a C. So that's good. Okay, so everything is checking out. P tracker is still not satisfied, so now our queue has 2 items. And A and a C. And our indexes are 2 and 4, which makes me uncomfortable. Because that's a difference of item 2, 3, and now 4. So we're going to go on to look at index 5, which is too far. That doesn't make sense. The start index is wrong. Should I have increased the start index here? At some point I didn't increment the start index when I should have. It happens every time in here, so it wasn't there. It happens every time here, so it wasn't there. So one of these conditions should have incremented the start index. What? You increment start index every time here. Every time here. So how's my start index only 2? Is this calculation incorrect? No, because in this test we only have correct letters. So it's not here that's wrong. Is there ever a case when I should have hopped 2? So here I basically get an off by one error, and that is why everything from here on is wrong. Whew. Man. Wow, 2 hours on this problem. So close. We got an off by one error with one particular case. So the question is, when should I have incremented and I didn't? Do I need to check here to basically say no? Alright, let's just look at the let's look at this. So when should I have incremented? So in here I say, hey, yeah, you can use me. Yeah, you can use me. Ooh, we already had you. So let's, and I see that you're the first one. So what let's do is let's just increment start index to there, and we'll forget all that happened. Okay, so there's our start index. We've already looked at that one, and we look at this one. We see it's an A. We say, oof, you know. Oh, here's the problem. Say, you know what? I should have fast forwarded to where? I should have fast forwarded my start index. Instead, what I did was I removed the first item and I started here, which so what should have happened? I said, we good. Ooh, let's just do a little swapperoni. Okay, so let's forget that other A happened, and you're my start index. You're my shining hope. And we look at this one, we should have said, ooh, no, sorry, not enough. So here, I should have set my start index to me, because I know that it's not you. So basically I could have fast forwarded, instead of just incrementing by 1, I should have fast forwarded until I popped my letter on. So another way to say that is, nope, not far enough. Here, we have a special condition. So here, we only increase the start index by 1 when these items are equal. I'm going to swap this because I hate this. Alright, so when the first Q just happened to be the letter, then that's a special case where we can only start 1. Otherwise, what we need to do here, and we could probably collapse this too, is we say, while, do it down here. While S at start index while Q dot peak well, no, here we go. While Q dot remove first. Here we go. This is it. Val first Q equals. It's another do while loop. You know, I love those. It's gonna get messy. So I'm just gonna kind of do this on down here because I think it's gonna happen in every case. So we say, hey, val first in Q equals Q dot remove first. Maybe I could say while Q dot size has size is greater than 0. First in Q equals remove first. And then if first in queue is equal to my letter, then let's go ahead and add the item to our queue at the end. I feel like I can do this ahead of time. Yeah, we'll do it at the end. There we go. So let's not worry about that. So if the first item in the queue is equal to our letter, then what? Then let's increase start index. Else, why does it not like this? First in queue equals, oh, that's why. So first in queue equals that. Then let's just increase our start index. Otherwise, let's increment start index and also add the item back to our P tracker. And at the end of all that jazz, we'll add our item to the queue. Okay, now let's try running all our tests. So basically, this has like a fast forward mechanism now instead of always just increasing by 1. Okay, we still have one error. What happened here? Still the same problem. Let's see what result we got though. So we got 2 results back. We got 3 and 4, but we didn't get 5. So we fixed the off by 1 error, but now we have a new problem. And I'm assuming this new problem is with the code that I just changed. So let's take a look at that real quick and see if we can figure that out without debugging. If it's not enough, while the queue size is greater than 0, pop the first item off of the queue. Oh my god, that exhausted the playlist. That's pretty bad. Oh my gosh, it's midnight. I don't see how many tests passed, by the way. How close did we get? 9 out of 36. Nice. Not very far at all. We remove the first item from the queue. If the first item in the queue is equal to the letter we're trying to add now, then awesome. Just what? Do nothing. Because I think we'll have already incremented it here. So if the first item so maybe I should call this one removed, because I've already removed it. So if removed is equal to removed first. So if the first item in our queue I think that needs to happen still. Otherwise, we see an item that needs to be added back to our tracker. Okay. And then we increment. I mean, that seems good to me. Let's set a breakpoint here. Oh, I didn't mean to hit all these tests. Let's see, just the failed test. So the first time I come through here, it's when we're looking at start index 4, okay? And our result index already has the result of 2 in there, so this one actually appears to do the right thing. Okay, we remove a B. That's fine. We increment start index to now 5. Okay, and then we should move on from here. Oof. Ooh, but then, well, poo. We're going to removed an A. What's left in our queue at this point? We're going to fast forward over the 5. So our start index is going to become 6. And we're never going to add it. So we drained our queue here, and we added our item back on. So now our start index is 6. Our result says missed 1. We missed 0, 1, 2, 3, 4, 5. Hey, that's invalid anyway. This should have been 1. This should have been 2. This should only have 2 values. What? I'm only seeing 2 C's in this whole thing. Did I copy the input wrong? Oh, there are 3 C's. Bab. This is not the right test. What? What the heck? My S is incorrect. Look at that. S has a D at the end. This S has a C at the end. So at some point my S got modified. CBAE. I'm looking at the wrong test. Like, what on earth is happening here? I must have been debugging the wrong test. Yeah, look at that. S is still wrong. CBAE, BAB, ACD. What? Do I have something hard-coded? CBAE. What? I mean, am I... So this is the first breakpoint that I should hit. Let's just try that. What? Why am I running this test? I didn't say to run that test. Okay, so that is confusing. I don't want to run anagram test. I want to run this test. What? Alright, I'll tell you how we're going to do this. Jeez. Alright, thank you. Okay, so this is the first case where we've got enough. Not enough. We're at start index of 0. That's fine. Start index of 1. That's fine. Start index of 2. We should end up good here, actually. So what should happen here is that we'll loop over. Oh man, this is a problem with my length. We shall see. So what I'm looking for is when my start index is equal to 5. Start index is 3. Start index is 4. Start index is 5. So we should see a match here. Okay. Our status is not enough. How did that happen? That's not right. See, at position 5, 0, 1, 2, 3, 0, 1, 2, 3, 4, 5. Oh, that actually is okay. We should have recorded the 4. Did we record the 4? We recorded the 4. Now our start index is 5, and I'm telling you that I don't have enough for the letter B. 0, 1, 2, 3, 4, 5. How do I not have enough for that B? How do we get all this way where I'm looking at a B and I'm telling you I don't have enough for that B? That B never got erased. That B never got added back. Oh gosh, I never... Here, when we see this letter, we should stop this loop. Oh boy. Alright, let's try this test again. Now we're good. Alright, let's try all the tests. Man, that was a fun one. And then I gotta go to bed. So watch me get a time limit exception. Hey, all green, all green. Alright, so that was a legit bug. And what do you know, the bug was not where I had my quote-unquote unit tests. Maybe if I had written more unit tests. They really do, they're so helpful on these long problems. And you know, I knew that this was going to be like this. I knew there was a lot of moving parts, so I knew it was very dangerous to... it was very likely that we're going to be spending a lot of time. Wow, only one. That's funny. I knew there's a high chance that we're going to spend too much time debugging. That's okay. So it looks like there's a bug in my code when there's only one item in P. So here, we should return all the values of C, of which there are, looks like 3, no, 4. And what did I return? Oh, I got an exception. So, saying that there should be 4. Either way, find single letter. So I'm not checking a boundary somewhere. All right. So when I say remove first, I'm always assuming that there is something first. But don't I check the queue size right above it? Oh, I also do it here. This is kind of weird. I'm assuming that I've added to the queue already at this point. This seems like a pretty bad bug, actually. So if it's satisfied, I say result indices, add the result. And for the tracker, I say, hey, add back the first item in your queue. Why do I say that? I mean, I should really just say add back letter, right? No, I need to add back the item. I see. So here I should be adding back the queue. So I'm tempted to just kind of special case. So if above all this jazz, if s or p dot length equals 1, then we just return s dot count p p. Type dispatch require a list. Oh, I need to find all the items where the item equals. What's the problem now? I returned a character. I need to filter, I need to get the indexes. This is dumb. Maybe I should just, what? I mean, I could just say, what? So in this case, the P tracker should add back my C. So if I just add this first, then I'm good. There we go. That should be good. And that's easier than my hacky workaround. Hey, look at all those. Alright, I'm nervous. I want to go to bed. $85 lines. I can't wait to see the top scoring answer and have it be like 10. Alright, right answer. Accepted. Okay, so I'm on the good side of things. What do the top answers do? For some reason I can't click. It's not letting me click. I want to see the top answers. There we go. So they kept an array of 26 and they kept the quantities there. So that'll be a better lookup. We saw this before. I made the same mistake. I could have done better by keeping it an array than keeping a hash. And then how do they check 0? Okay, they literally go through and count the items. Okay. Is anagram function. So they literally, man, this is much simpler than mine. They literally just run through every item and check it. Wow. They compare two arrays. Okay. So they normalize the arrays to characters of 26 and then they run through. I'm surprised that ran faster. I guess that one was in line with mine. Or it wasn't that far off. I don't know. Kind of far. Another int array, 26 characters. So first they go through, link the P and they create a hash table like I did. Okay. And then wow, the end is less than the length. Okay. They check each item in the hash. And then they decrement it just like I did. Okay. Oh, that's smart. They don't have to reset their hash. They basically just either decrement or increment it. That's good. That's smart. It means I had the fast forward mechanism, which they didn't have to worry about. So the code ended up being cleaner. So that's nice. Okay, yeah, so that's slicker than mine, but I consider optimization. Same rough algorithm, it's just a better implementation. I'm okay with that. Alright, let's see the discussion on this one. So this one took me, I can't see the solution. Oh, I just want to see the discussion. Alright, sliding window. Maintain a map of type integer. Okay. Sliding window on each. Okay, window start, window end. So. Okay, I mean, that's essentially what we did. I wish I had thought about it in terms of a sliding window, though. It might have helped me with some of that terminology I was struggling with. Okay. Yeah, that window start, window end. Huh. Okay, that's pretty slick. I like this whole checking to see if both need to increment because the item wasn't found. Complexity, space complexity. Oh, okay, yeah. Okay. That's a technicality. Alright, fine. Yeah, my hash table also had a bounded space of 26. So you could argue that my space complexity was also O of 1. Wink, right? My hash table would never have more keys than 26. Fine. So yeah, I could have done better by using an array. It's true. It's true. Yeah, and this is basically the same solution that we just looked at where it either increments or decrements. So yeah, that's cool. All right, well, hey, I'm gonna go to bed. Thanks for hanging out. Sorry it took so long. We've got a couple weeks left, so just like last month, it seems like they really ramped up the difficulty in the last couple days here. So whatever, you know, I learned some stuff. I wish I had used the int array instead of a hash table, and I wish I had thought about this in terms of sliding windows. I think it would have, it just would have meant less invention. And I think if I thought about it in terms of sliding window, then I probably would have just had an easier time. So my solution overall, I'm happy with the algorithm, but it's just big. I had this whole separate class, which did make testing easier, so I'm not actually unhappy with that. So it was very nice to be able to have this and be able to test this in isolation. So I think that saved me time, but that's definitely something that took a lot of time. But I'm much happier to build test cases than I am to debug off by one errors. So I ain't complaining. Time well spent, methinks. All right, y'all have a good one. Thanks for hanging out.